we are more accurate, and also the speed is better than comparable software. This is what our customers say. This is also a sign where we are coming from. So our main applications are lubrication cases. The case which we are exploring today, on the left side you see our simulation domain. We are exploring a gearbox. Visually it looks already good, but we can also set the sample window, so we want to look at the sample windows. This is just a little bit more stable than directly use a constant. In both cases, in the experiment and in the simulation, we don't have any lubricant in the middle and in the input bearing.
Advanced simulation drives engineering innovation, a gearbox lubrication with shonDy. I'm super excited to see what you have presented to us, or will present to us today, Moritz. shonDynamics, or shonDy, one of the tools from shonDynamics, can simulate various physical properties of fluids within a three-dimensional space. Users can easily launch a simulation once they imported their CAD geometry models, configure the movements of the bodies, and set up the physical properties of the involved fluids. In comparison to many other CFD software, shonDy does not only require mesh generation for the simulation domain. Without mesh constraints, it is much more flexible in many simulation scenarios. It has particular advantages in simulating free surface scenarios, such as splashing and spraying, and when moving bodies are involved. So I'm super excited to see what you've prepared today, Moritz, and welcome to the show.
Thanks, Josef, for your kind introduction, and welcome also from my side. Good afternoon, good evening, good morning, wherever you are. My name is Moritz. In the next couple of minutes, I will show you our tool shonDy and how we solve problems like gear lubrication with this kind of tool. In the first few minutes, I will have some slides to show you who we are and what the case will be. Then we will switch directly to the tool. So who we are. We are shonDynamics. We were founded in 2018. Currently, we have offices in Karlsruhe, and maybe if you already guessed, I'm from Karlsruhe, and also Suzhou, China. We are currently around 80 persons in the company. From there, around 50% are developers. We are mainly active in the field of electric vehicle. So Josef already introduced shonDy, our tool we show you today, and we are exploring today together. So yes, it's a mesh-free particle CFD tool based on the so-called MPS method. I think most of you who are already used to some kind of these tools, who are not only in traditional CFD, but also in particle CFD, they are more used to SPH methods. Comparing to that, moving particles simulations are similar. It's only an additional pressure solving step there. We have fully coupled fluid-solid interactions and also multi-body dynamics included in the tool. And for sure, we can calculate on GPU and CPU and all in parallel. So the case which we are exploring today, on the left side, you see our simulation domain. We are exploring a gearbox. On the right side, it's the input shaft, and on the left side, it's the output shaft. And from the engineering point of view, we want to see if the bearings are suitable lubricated without any active pumps or something. So everything should happen passively. So the idea is that we have on the bottom of our gearbox the lubricant. This will be carried by the output shaft to the small pool on the top of the gearbox. And from there, via the channels, the small channels will directly guide the lubricant to the bearings, these three bearings. And we will also compare our simulation results to experimental results. And you can see on the right side at ambient, on normal temperature, the results on the right side, so at room temperature. These are the experimental results. So I hope you get an idea what I want to show you now, and then we can directly jump to our software. So if you open shonDy for the first time, or you will see this kind of welcome page, and then we can make a new case. As a short disclaimer, I reduced the resolution of my screen a little bit, so the buttons are larger for you, and so you can follow better what I'm doing. So if the buttons are a little bit unnatural large, it's because I want to show you what I'm doing. So this is a fresh case now, and the idea of our workflow is if you start from top to the bottom on our workflow tree and you reach the bottom of it, you will have a finished case set up, and you should be able to run the simulation. As you already see here, we have two default materials, and our default material on the fluid side is lubricant oil. So this is also a sign where we are coming from. So our main applications are lubrication cases. On the fluid and also on the solid materials, you can always change the properties of the fluid and solid. So density, kinematic viscosity, and these kind of stuff. Because we also say today that we are exploring very low temperature cases, and in case of, or in the sense of fluid dynamics, this means mainly changing the density and kinematic viscosity of the fluid. For setting up, I will keep our default material, lubricant oil and steel. Solid materials are mainly have to be changed if you have some swimming cases, so you need the density, and also if you have some heat transfer cases. So, but today we don't have any heat transfer, so also steel is completely fine. So the first step would be now to add our geometry. Here we can see all the selected geometry and also the unit. So it's an STL file now. And sometimes if you export it in a wrong unit, you can change it here back to the correct unit, so you have the correct dimension. This takes a few seconds because the solids are validated and see if everything is correct. So again, we see our gearbox I had already on the slides. Input shaft, output shaft, and everything else. So this is already the import of our geometry. We see here on the scale that the importing also worked fine, that we are in the correct unit system. Then maybe just changing a little bit of the fluid domain, the computational domain. This means that only what happens in this area will be calculated. As a next step, we have to add a fluid. We have basically two systems how we can add fluid in shonDy. Some either by add by file. So there a second STL file would be added, which is the outline of our fluid. But today we will add it by liquid level. This will, and here we can, if we activate the widget, we can see the liquid well, and then we can just drag and drop it where we want to have our liquid level, and also decide what kind of fluid we want to use. So if we had here different kind of fluid, so we could also change it here. So this is our liquid level now. The only thing what we have to watch that this little ball is inside the fluid domain. So if the ball would be inside a gear, for example, then shonDy would try to generate fluid inside of this gear and not inside the fluid domain. So this has to be always inside of the fluid domain. another thing is, if I had it like that, then the fluid will be filled up until the liquid level is reached. If I just want to have a specific volume, I can also add it like that I'm type in directly the amount of fluid I want. So in this case, 300 milliliters. So this means that we will add fluid from the bottom up to the liquid level. But if we reach 300 milliliters earlier, then it will stop to generate fluid. So this is basically it. So we have already the fluid settings and also the solid. But for a gearbox, we need the rotation and the moving parts. So now we have to add this part. This happens via our joint widgets. We need a rotation. I switched this one off so you see it better. So this will be the input shaft. So this is the active rotating part. So we can, from a drop down, we can choose which gear we want. So this one, and the rotation center should be from this body. So it will set inside at the mass center of this point, and also the rotation axis. So we can see here now it's perfectly aligned with our input shaft and the rotation speed, and the rotation speed. Yes, this is the next thing we have to add, is the rotation speed. This happens. We have two different options, either constant speed or time-dependent speed. I always recommend to our customer to add a time-dependent speed, so to add a small ramp to it. This is just a little bit more stable than directly use a constant rotation speed. Here we can show how we set it up. So we ramp up from 0 to 0.1 seconds up to 1,450 rounds per second. And also we can see here the direction it will rotate. If we want to have the different kind of rotation, so this is counterclockwise. So if we want to have it in the clockwise, we could change it by changing the axis. But today we want to have it like that. This is now the rotation of the main shaft. And then we also want to add that there's small bearings, to rotate together with our input shaft. So this is pretty easy here. We just have to select our bearing we want to have, and this is it. So this will rotate now together with our input shaft in a speed factor of 0.5. If we want to have a different speed factor, we can change it also. And maybe you already recognize that on the left side, we get this every solid we choose, and we set a rotation speed or some rotation, we get a small gear here. So this means that from now on, these are moving bodies. So the middle and the output gear is missing now. This happens not by active rotation, but if we just use a gear link. And the gear link means that the input shaft is putting the velocity, the speed in, and the rest will follow. For that, we have to choose first our active gear as the body 1, and as body 2 our middle gear. So now they are linked together, and the gear mid is also moving body now. We have to also add the rotation axis. And now to calculate the correct speed of the middle gear, we have to set the gear ratio or the T's number. I have to look up at my cheat sheet. This one have 21 teeth, and the other one has 47. And also add our bearing. And we have to repeat this with the last one. So there now the active gear is now the middle one, and the following gear is the output one, adding the axis and also the number of teeth. So this means that this gear will has 22 teeth, and the output gear has 61, and also the bearing for the output shaft. So this is our case setup. From now on, we could just hit run, and then we would have a running case. But monitoring is also important. So we have to know, is our case more or less in a steady state? Can we draw conclusions from our simulation results? So monitoring is also always important. For shonDy, we have 3 different kinds of monitoring points, lines, and windows. Today we will use the window sampling. There we have 3 different kinds of, 4 different kinds of sampling window, and we use today the cylinder as a sampling point. The idea is to put the cylinder inside of the bearing, so we know, is the bearing sufficient lubricated or not. So this means that we have to select the middle shaft, and then we put directly the sampling winding inside the mass center of our input shaft. Then we just have to change the rotation and make it much smaller. And move it to the correct position. That's too far. And so in a real case, we could make it a little bit more, more fine, but I think you get the idea how the sampling setting of the sampling window works. We can duplicate it and move it to the other side. So now we have 2 sampling windows inside the 2 input bearings. The same we can do it for the middle shaft. Then I will stop because it's just repetitive work. That's much too. So this would be the setting of the samplings. Now we would have to repeat it for all different bearings, and then we would be finished. The last part is to decide how long the simulation should last, so for 5 seconds or 10 seconds as you want, and how often we want to write our results, so the 3D results and the sampling points, and also decide how long or how large our particles will be. I decided I have to look up. So together with this particle size and with the amount of fluid we put inside the gear, we will get around 2 million particles in total. when I talk about particle numbers, I always talk about only numbers of the fluid side, because we don't need any particles in the wall. So this is just fluid particles, so 2 million fluid particles. And yes, this is it. This is the setting up of our gearbox case. For comparison, we should now calculate for 25 degree and also for minus 40 degree if we want to have really low temperatures. And yeah, because this is an industrial case, this would take now for around 12 hours to 1 day as calculation time. So we don't have time for that. So as in a good cooking show, I already prepared something. And we can directly jump to our results. I hope this is now, yeah, this is our result. So if you now would be finished with your calculation and would first time look at your result window, it would look like that. We can hide it. We can see the fluid at time step 0. And then we can have a look how the fluid will be carried up to this pool. So we don't have to wait that long. We can directly jump to a later part of our simulation and hide a little bit of our casings. And yeah, what do we see here now? That the pool gets filled by the lubricant, and from there we have a flow from the pool to the middle bearing and to the input bearing, and also from there to the output bearing. Sorry. So visually it looks already good, but we can also now we set the sample window, so we want to look at the sample windows, and here we see the amount of fluid inside the samples. And we can see now this is we see already that most of the sampling get fluid except one bearing. This one gets, in the whole 10 seconds of simulation time, we don't get any lubricant. And if we look at our results, this is this bearing. Sorry, I used to say it wrong, not correctly. And we can see that from there to there, there's no channel, nothing. So we can see that this is not supported, and therefore we don't get any liquid to this bearing. And this would be now one suggestion to improve our gearbox, to make to change the solids that way, or to our body, our gearbox casing that way, that also a channel will be going to this output bearing. So this would be like how you can do the post-processing in shonDy by different kind of 2D charts, and also by the 3D window. And the last one, because it's not always like you want to have sometimes also really nice pictures. So also a rendering tool would be nice. So we included also a rendering tool to shonDy. We can jump here now to later where something happens. So this is our fluid. This should be lubricant oil in red. So, and if we click on the render button, we have first to change our camera settings. So, and then we can start our render preview. And this is in low. We can change it. I will change to, let's make 4K. And change it. Change a little bit of the brightness. And yeah, this would be our rendering tool. Also, we could change different maps, but I always recommend first, this is first to change it to low. So it's better it's faster, and you see, you can change it and have the point of view you want to choose, because 4K needs always a little bit time. So it's better like that. Okay, this would be also the rendering. So if you need, if you need really nice images for your presentations or for your boss. Now let's look at some deeper results. So this would be how shonDy work. And let's go to the comparison of our results. Now I'm jumping back to the presentation. So this would be our basic results. This would be our render results. And this is our experimental result. And if we want to compare it in more detail, we can look at the ambient temperature, so at 25 degrees Celsius and at minus 40 degrees Celsius. And both the front view on the left side, the experiment, on the right side, the simulation. And if we just compare it, we also see directly, okay, that the output shaft is working, that there will the bearing get filled like in the simulation, and also the middle and the input shaft. If we compare it now to the minus 40 degree, where the viscosity is much higher, we get only fluid inside the output bearing. And also in the simulation, if we change it, there the distribution is a little bit different from the simulation. So here we have more or less a horizontal filled bearing, but in the simulation we get the lubricant distributed around our bearing. But in both cases, in the experiment and in the simulation, we don't have any lubricant in the middle and in the input bearing. And why is it this like? This is, if we look at the top of our gearbox, we can see in the 25 degree case, the pool gets filled properly in both in experiment and simulation. But if we look in the experiment of minus 40 degree and stop the video, we don't see any fluid enters this pool on top of the gearbox. And if we look at the simulation, at the beginning, we get a little bit of fluid, but in the later stage of the simulation, we don't get any more fluid into the pool. So also know that the channels don't get filled by lubricant. So the reason for that is that at the beginning of the simulation, we have all the liquid at the bottom of the gearbox, and then the lubricant will be get distributed around the gearbox, and then it's not enough fluid left to fill or to carry by the output gear on top of the gearbox and into the pool. So this is how shonDy is able to calculate properly the distribution of lubricants in gearbox in that different kind of situation, like in this extreme conditions like minus 40 degree or at normal temperature. And in both cases, we get good results in simulation compared to the experiment. This is now my, I hope it was not too fast and it was not, you got what I wanted to say. And idea of shonDy and how shonDy works. And maybe if now you get interested in shonDy, you can always, I hope, maybe you could post a link in the chat for our free trial. So you can go to and contact me, and I will respond to you, and then we can talk about if you want a free trial or not. Yeah, thank you, Yusuf, for giving me the stage. And if there are questions, I'm happy to answer them.
Sure. Thanks a lot, Moritz. Appreciate it. Really nice demonstration. Of course, this was one of the many use cases, Moritz, right, when it comes to what shonDy can actually do. You have also different applications and capabilities of shonDynamics.
Sure. It's but I wanted to make it complicated enough that it's not too simple, but also simple enough that I can show you in 20 minutes to 30 minutes something which can be followed, and not only, it shouldn't be too overwhelming and not too simple. So I think this is a sweet spot for this case.
I like that, Moritz. This is really good. And obviously, anyone who's interested in the technical capabilities such as GPU and CPU use, etc., and the method behind all of this, which is not a volume of fluid or anything similar that you might heard of from other classical CFD tools, I'll discuss this tomorrow with Martin, the CEO of shonDynamics, in our podcast. So if anyone is interested, make sure to listen to that as well. So you can basically build the bridge between the demo that Moritz has shown you today and kind of the technical capabilities that Martin will talk about in tomorrow's episode. Apart from the gear lubrication system, Moritz, are there any other particular use cases that you're very excited about, what you've worked on in the past, or maybe now?
I think in general, I like this water management around cars very much. I think it's always interesting to set it up, and I think water management around cars are a little bit my sweet spot to make them happen. And car waiting cases like this, but also EDU cases we had a lot in the past. So EDU, it means the gearbox and the e-motor combined together, and see the lubrication in these kind of applications. Yes.
Exciting, super exciting. I've actually posted the link of your case studies, Moritz, in the chat, so people can actually check it out. And also the chat, the link for the free trial. So shonDynamics.de/contact/trial equals true. And then I'll just go to the website, shonDynamics.de, and hit request trial in the top right corner. And apart from that, if people want to check out shonDy and other products that you offer, shonFlow, shonMesh, etc., they can also do that on the website. And as I said, we'll have a dedicated session with Martin tomorrow when it comes to kind of the technical capabilities, the background, the mathematics behind all of this. And it's probably one of the most impressive things I've seen, especially your renders, Moritz. Martin, so props to you guys. Really, really great work. And if people are interested in getting to see more use cases, maybe even case studies or setups, let us know in the comments, and we'll make sure to maybe cover something else or another use case in the future. Excellent. Cool, Moritz. One last question we actually got from YouTube, which is, could you give us kind of your unique selling proposition? So what is shonDy better at compared to your competitors when it comes to SPH/MPS software?
It's like, it's always difficult to say what we are, or it's not, I don't want to call arrogant, but I think from our customer, what we are hearing is that we are matching the simulation, the experiment better, and we are more accurate and also the speed is better than in comparable software. But so this is what our customers say, not what.
Okay, so we can just agree that basically you guys are doing excellent work and doing a great job when it comes to actually rolling out the software and matching experimental results, but also when it comes to speed. But again, as I said, I'll talk to Martin tomorrow about kind of the topic of CPU versus GPU, the mathematics behind all of that, because speed is not everything. Of course, accuracy is also really, really important. So I'll talk to Martin about that and really dig deep on what you guys are actually working on. Maybe he'll share a couple of secrets and some insights of shonDy and your other tools. Moritz, thanks so much. I'm looking forward to a second session, hopefully in the near future. This will be post-edited, so I'll put it on my YouTube channel, so our YouTube channel, and also shonDynamics will most likely upload it on theirs. And thanks a lot for joining today. And Moritz, again, thank you so much for the session.
Okay, thanks.